Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Leay. High entropy alloys have garnered a lot of attention for their unique properties that aren't completely understood. One interesting aspect is the sluggish lattice diffusion effect, where very different sizes of the component atoms greatly distort the crystal lattice, leading to energy barriers for atomic diffusion. One research team has made use of the sluggish lattice diffusion effect to create high-strength alloys using nanoparticle strengthening.
We mainly focus on the innovative design of the advanced structural material. So we need this kind of the material to be very stable at the high temperature. For this material, the first problem is thermal instability of this kind of material. The precipitates, actually is the nanoparticles, right, go to be dissolved at the high temperature. So how to make this nanoparticle to be stabilized at the high temperature is the key motivation.
That was Tao Yang from the City University of Hong Kong in China. His team has been looking at an alloy of nickel, iron, chromium, aluminum, titanium and tiny amounts of boron where up to half of the nickel was replaced by cobalt. The team found that nanoparticle growth at elevated temperatures, up to 1000 degrees Celsius for a maximum of 240 hours, was inhibited by the addition of cobalt. Additions of 15 and 30 atom percent were tested. The nanoparticles were comprised of titanium, aluminum and nickel, forming an L12 crystal structure, whereas the matrix was a face-centered cubic into which the iron and chromium as well as some nickel partitioned. The cobalt also tended to partition into the matrix. The elemental mapping was used as the basis for kinetic modelling, where volume diffusion and diffusion across the interface were considered.
We can find that the cobalt elements play a significant role in inhibiting the growth of the nanoparticles. So we find that when the cobalt elements go to the 15 or 30 concentration, and it's controlled, the elements is dominated by the lattice diffusion.
Without the addition of cobalt, diffusion across the interface with the matrix controlled the coarsening of the nanoparticles, but when cobalt was added to the alloy, at either 15 or 30 atom percent, a different mechanism was dominant. The kinetic modelling also shows that the addition of cobalt strongly affected the interdiffusion of aluminum. Atomistic simulation using density functional theory showed that cobalt atoms, when located in close proximity to aluminum atoms, increase the energy barrier for the aluminum.
Cobalt will inhibit the mobility of aluminum elements as well as other elements. So DFT showed that is why the cobalt can make the aluminum to be so difficult to move.
These results not only support the development of advanced materials that possess excellent strength at elevated temperatures, but also provide insight into the properties of high entropy alloys.
For high entropy alloy, a lot of studies has claimed that there is a sluggish diffusion effect, but the problem is that it's not the case for all the alloy system, only for some specific alloy compositions and also the concentrations. So for our studies, that is most important thing that we find out what is the most key elements for the high entropy alloy, and to find out the origins, that how to control this kind of the sluggish diffusion effect.
Nanoparticles have already been seen to improve the strength of materials, and now Tao Yang's team has provided insight into how this can be achieved at high temperatures. This work was published in a recent issue of Nature Communications. My name is Leay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.